Let's talk about the consequences of the first law of thermodynamics. In the derivation, Cv is equal to partial U over partial T at constant volume. We considered that the internal energy or the change in internal energy with respect to volume at constant temperature is zero. Okay? In other words, we assume that U is only the function of temperature only. Okay. So Gay-Lussac and Joule attempted to test whether or not this internal energy depends on volume at constant temperature. Okay, they wanted to see if they can get any change in internal energy when you change the volume, keeping temperature constant. Okay, or in other words, you can also say they tested to see whether this is true or not. Okay, so they found that the internal energy is a function of T only, and it does not depend on the volume. Okay, that's what they found. This is true in their experiment. So this property is only approximately true for real gases. Okay, we assume that this is completely true or exactly true for ideal gas, but for real gas it is not completely true. It is only approximately true. Okay, we'll show that later. So in order to find this out in experiment, we cannot actually measure internal energy directly in an experiment. Okay, so we need to express this expression in some other quantities, some other measurable quantities. Okay, so there are lots of things in thermodynamics that we cannot measure. So whenever we cannot measure anything in thermodynamics, we usually express those unmeasurable things in terms of measurable quantities. Okay, so one way to do that in thermodynamics is by using the cyclical chain rule, which is so if you have this function U is function of V and T, then you can write this as partial U over partial V at constant T times partial V with respect to partial T at constant U times partial T partial U at constant V is equal to -1. So this is what we are trying to measure in an experiment, but we cannot actually measure that directly, so we want to express that in terms of other partial derivatives. So we can write this as 1 over partial V partial T at constant U partial T partial U at constant V. Okay, and then we can measure this one. This is basically how temperature changes with a constant volume, or volume changes with constant temperature. Okay, so we can just flip this and write it as negative dt dV. It is basically change in temperature with respect to change in volume at constant internal energy. If we could maintain constant internal energy somehow in an experiment, then we can easily measure that. Okay, and we can also flip this one, partial U partial T at constant V, and by definition this is nothing but it's CV. Okay, so we can write the partial U partial V at constant temperature as negative CV times partial T partial V U. Okay, we can measure everything in on this side. Okay, so these are all measurable. That means if we know the terms on the right side, then we know this term on the left side. So what we need to do now here is need to keep the internal energy constant in an experiment. Okay, and we need to measure the temperature by changing the volume of the system or of the gas. So the question arises now, how do we keep the internal energy constant? Okay, so we need to figure out how to keep U constant. So the basic idea to keep U constant could be explained from the first law of thermodynamics. So we have dq is equal to, or let me write small q here, small change in q, dq, or not change, small q, small heat is equal to small change in U plus work done, small amount of work. Or we can also write this as du. Now we don't need this bar on du because du is exact differential, so that's not the bar. Okay, that's exact differential. So du is dq minus dw. Okay. So if we could somehow make it an adiabatic process, somehow we don't allow heat to enter or escape the system, and we don't do any work on the system, or the system doesn't do any work, then we get internal energy to be zero. Okay, that means we want a process, some kind of process in which there is no heat involved, or we want an adiabatic process. Okay, so we need adiabatic process, and there shouldn't be any work, no work done on or by the system. System here is some kind of gas. Okay. So Joule did this experiment in which there is no heat involved and there is no work done on or by the system. So for his experiment, what he did was he have this cylinder, and the cylinder is insulated, or you can say it has this adiabatic wall. There's no heat entering the system or exiting the system. So that's adiabatic wall. And he created partition between the left and right chamber. he partitioned this cylinder into two parts by a very thin diaphragm. Diaphragm, diaphragm, diaphragm. Okay. On the right side, he fills some gas. Okay, the gas has volume V naught, and the gas is at temperature T naught. On the right side, he created a vacuum. Okay, there is no gas. He didn't put anything, so it's only vacuum, and it has volume of, say, V1 minus V naught, where V1 is the volume of the entire system. Okay, so this is vacuum. And here he put some gas. So somehow he breaks this diaphragm, and when the diaphragm ruptures, this gas undergoes free expansion. Okay, free expansion means now there's no work done on or by the system, because there's nothing to do work on. So the gas just expands without doing any work on the system, nor there's any kind of work done on the system. Okay, so there is free expansion of gas when the diaphragm ruptures. And after the expansion, the final volume and temperature of the gas is V1 and T1. Okay, so that's the final state after the rupture of diaphragm. Again, there is no heat entering the system, as well as there is no work done in or by the system. So that means du is equal to dq minus p dv is 0. Okay, this is 0, that's 0, so internal energy is 0. Now we are keeping the internal energy of the system constant. So in this expression, we wanted to keep this internal energy constant, so that's how Joule kept the internal energy of this system constant. So we can measure the final temperature of the system. So by using this fundamental theorem of calculus, we can write integral of some rate of change of a quantity du dv at constant u dv, okay, at t1 from t1 to t2. This is given by t2 minus t1. Okay, so that's the fundamental theorem of calculus. So basically f of x dx is equal to fb f of b minus f of a, where this f of b is, where this one is rate of change of this function. Okay, so this is exactly same kind of expression here. So that means we can find the final temperature. Let's say final temperature is T2 in terms of the initial, this is T1, initial temperature. Okay, so let's just call initial temperature T naught plus T1 to T2 dt dv at constant u dv. Okay, so basically he measured the temperature by changing the volume, keeping the keeping this U constant. Okay, this is what he measured. Measure temperature by changing volume. Volume is changed because the gas expanded after the rupture, and keeping U constant. So he called this coefficient, this integrand, the integrand in this expression, Joule coefficient. Okay, so Joule coefficient denoted by this eta is partial T partial V at constant U. So in his experiment, Joule was unable to measure any temperature change in this experiment. So there was no any kind of temperature change. He found this to be almost zero. So he used various kinds of gases. So Joule used various types of gases, and he found that this temperature change in this experiment was very, very small, okay, almost negligible for all the gases. So the value of the Joule coefficient in his experiment was less than 1000 of Kelvin per kilo, 1000 of the Kelvin kilomole per cubic meter. Okay, it's a very small change in temperature. So this is for the ideal gas, but if you look at the real gas, although the effect is small, but you will see finite change in temperature, okay, for real gas. So you can show this. There is a numerical problem where you will be asked to derive this. So this eta for real gas is partial T partial V at constant U is given by negative A V square CV. Okay, we will do this, we'll prove this in our problem solving session on Friday. Okay, so this is non-zero value. However, for ideal gas, if we are talking about ideal gas, then this A is zero, right? Because in van der Waal, P minus A V squared, V minus B is equal to RT. So this will be converted to this PV equal to RT for ideal gas when this A is 0 and this B is 0. So for ideal gas, this A is 0. When A is 0 in this expression, we get eta is equal to 0. Okay. So that means we can say that for ideal gas, U is the function of UT. Okay, so this is exactly true for ideal gas, and it's approximately true for real gas. Okay, there is some small finite effect of change in volume on temperature in case of real gas, but for ideal gas there is no any effect. Okay, we can show this also analytically, okay, or theoretically. So let's do that. So last time we showed this expression for small change in Q. So again, we are proving this Joule's coefficient. So that's T. At constant U to be 0. Okay, we want to show this analytically. Analytically means to the derivation, okay, not to the experiment. So we showed this last time, we got that. You can look back previous lectures before and you will find this. So du dt at constant v dt plus du partial u partial v at constant t plus p dv. Okay, so in this case dq is inexact differential. It's not a state variable, but mathematically there is a way to convert an inexact differential into exact differential, okay, by multiplying it with some kind of integrating factor. So our problem is to find an integrating factor with which if we multiply the expression or the quantity, then the quantity will turn into exact differential. Okay, so we will not show how we get this integration factor here, but I will just write the result here. So our integration factor here is 1 over t integrating factor, and if we multiply this dq by 1 over t, then this dq will be turned into exact differential. Okay, so then this quantity dq over t now would be exact differential. So we are multiplying both sides by 1 over t to make this dq exact differential. So 1 over d du dv t plus p dv. So this is of the form dz is equal to m dx plus n dy. Okay, so consider that dz is an exact differential. This is exactly of the form of this one, where m is that is m and that is n. Okay, and dt is dx and dv is dy. So what is the condition for exact differential? We talked about this a few lectures back. So if dz is exact differential, then it should satisfy this condition: dm partial m partial y is equal to partial n partial x. If this condition is satisfied, then dz is exact differential. So here our dq t is exact differential, so it must also satisfy this condition. So that means let's look at our expression here. So that means d partial v, our m is 1 over t partial u partial t at constant v, okay, is equal to partial t, okay, partial t, and then n is 1 over t du dv T plus P. Okay. So just to make it a little bit simpler, I will, for an instant, I will not write these things, V and T constants. Okay, it's obvious. If we write partial U partial T, that means we are keeping V constant. If you write partial U partial V, then that means T is constant. Okay, so I will just not write that for now. So we have partial V 1 over T partial U partial T, that is equal to partial T 1 over T partial U partial V. Actually we don't need to write that, plus P. Okay, so here this partial with respect to V means we are keeping temperature constant, so we can pull this T out, and we have this partial 2U partial V partial T, that is equal to, here we are keeping volume constant, so that means we need to take the partial of 1 over T also. That means we need to use the product rule. So 1 over T partial 2U partial T partial V plus, and when we take the partial of 1 over T, we get 1 over T squared, so partial T, and then for 1 over T, P 1 over T, it would be plus 1 over T partial P partial T minus 1 over T squared d partial T P. Okay, so this quantity and this quantity are same. When you just flip this dt and dv, you get the same thing. Let's put missing a quantity here, so here we should also have du dv. Okay, so let's bring this on the left side, so 1 over T squared, that's cancelled, so partial U partial V, this is at constant temperature, and that's what we are looking for. That is equal to 1 over T partial P partial T minus 1 over T squared, that cancels, so times P. So we can multiply both sides by T squared, so multiply by T squared, T squared, T squared, so these T squares cancel, these T squares cancel, and that cancels, so we have partial U partial V at constant T, which is the Joule's coefficient, that is equal to T dP dt minus P. Okay, so now for ideal gas, the equation of state is given by P is equal to RT over V. So this Joule's coefficient would be, then taking the derivative of this with respect to temperature, would be RV minus P, and then TRV is P minus P, so eta is 0. Okay, so this is the analytical derivation of the effect of change in volume on change in internal energy at constant temperature, which is 0. And here we are using the assumption that this thing is the exact differential.